In this video, we're going to be looking at topic 15C, the carboxylic acids, and this is part of Unit 4 of the IA2 chemistry course from Edexcel. So we'll be looking at the nomenclature and the structural, displayed and skeletal formula of these carboxylic acids, how their physical properties are affected by things like hydrogen bonding, specifically looking at boiling temperatures and solubility, as well as how we prepare carboxylic acids and 4 key reactions. So the first thing we need to look at is the functional group. So our carboxyl functional group is a carbonyl with a hydroxyl group also attached to the same carbon. So we have our carbonyl and an OH group attached to it. And that can be attached to any R group. So our general formula is RCOOH. Now the suffix that we use for this is anoic acid. So we have methanoic acid, ethanoic, propanoic, and so on. As with the previous aldehydes and ketones, we also had a common name that you may have seen, so probably acetic acid may be the one that you're most familiar with, but we want to focus on the proper IUPAC names, so methanoic, ethanoic, and so on. It is very important that you can draw the full displayed and skeletal formula of these molecules, and you need to know the key molecules being the first 4 plus any branching. So something like methyl propanoic acid containing that branch. And you should be able to draw them in skeletal and displayed, which is something that you've been doing since year 12 of A-level and drawing display formula since GCSE. So this shouldn't be anything new, but you might want to practice this. When we look a little bit closer at the bonding, we're going to focus our bonding on the functional group. We know how the carbons and hydrogens of the hydrocarbon part bond, but we want to focus on the carboxyl functional group. And what makes this very different is the fact that we now have 3 polar bonds. We have dipoles in the carbon-oxygen where it's the single bond, and of course the oxygen-hydrogen, with the oxygen being the more delta negative of each of these because it is the most electronegative. So what we tend to find is that most of the reactions of this group involve the loss of this hydrogen to form what we call the carboxylate ion. So if we start off with the carboxylic acid, we draw out all the bonds, we can see that this carbon is delta positive, our oxygens are delta negative, and the hydrogen is delta positive. But when we undergo a reaction, we're going to lose that hydrogen. So this becomes delta negative. That oxygen is still delta negative and delta positive. But rather than having a double bond, what we actually see is the charge and the double bond character being spread across both oxygen atoms. So we get something that looks a little bit like that. So that dotted line showing that the charge is spread between the 2 CO bonds. And this is our carboxylate ion because it's that negative charge. And it's formed when we've lost that proton. Now, as with the aldehydes and ketones, carboxylic acids have very distinct smells and they have particular sour tastes. You are not expected to memorize these smells or sour tastes. It is just for your information, but the ones that are probably most key are ethanoic acid, which is in vinegar, so it gives it that sharp taste, and citric acid is what gives lemons their sour taste as well. When we look at the actual boiling temperatures, what we see is that the polar bonds in the carboxyls give us very strong intermolecular forces. So we get hydrogen bonds plus permanent dipole bonds and London forces. So we're seeing all 3 different types of intermolecular bonds here. And we get London forces, of course, in the hydrocarbon chain as well. So what we find with the carboxylic acids is they have even further elevated boiling points in comparison to the other homologous series that we've seen. So we would have the alkanes and alkenes at the very bottom, then the aldehydes and ketones because they form the permanent dipole, alcohols because they can form hydrogen bonds, and then carboxylic acids because they can form even more hydrogen bonds. So they have, in particular, quite high boiling temperatures in comparison to other organic molecules with the same molar mass. And as we've seen for all of these homologous series, the larger the molecule, the more your boiling temperature increases. And we know that that's due to the increased London forces between the electrons and between each of the different atoms. The other physical property that we have to know about is, of course, solubility. We've seen this with the aldehydes and ketones and with alcohols, so the carboxylic acids are no different. And what we find is that when they are short chain, they are very soluble in water because the polar bonds that exist can form hydrogen bonds with the water molecules. So if we take ethanoic acid, where we have our CH3, our carbonyl group, and our hydroxyl group, of course we know that this is delta negative for the oxygens and the hydrogens are delta positive. So the delta negative oxygen is going to attract delta positive hydrogen of the water. And we're going to get hydrogen bonds forming there. But we also get hydrogen bonds forming between the hydrogen of the carboxyl and the oxygen of the water with its lone pair. So we're forming two different hydrogen bonds here with the carboxylic acid and the water. Therefore, it is very soluble. The problem is, as with the aldehydes and ketones, as our chain length increases, the solubility decreases, and that's because the hydrocarbon chain becomes more predominant. So that force from the hydrocarbon chain overpowers the force from the hydrogen bonds, so it makes them less soluble. It's important that you're able to draw out the diagram of the hydrogen bonds. Of course, you've been doing that since topic 7 back in year 12, so please make sure that you can do that again because it could come up in unit 4. So let's just pivot and look at how we actually make these carboxylic acids. We've seen some of these reactions before, particularly back in topic 10 when we looked at the alcohols. So we can have a preparation of a carboxylic acid by oxidizing either a primary alcohol or an aldehyde. And the reaction is carried out under reflux this time. So the reflux diagram is shown on the right hand side here, and you can see that the main difference is our condenser is vertical. So anything that becomes vapor goes up into the condenser, goes back into our liquid and drops back down into the round bottom flask. This is of course different for an aldehyde where we want to use distillation. So we carry out the oxidation here under reflux so that we get complete oxidation or full oxidation to make our carboxylic acid, and the most common oxidizing agent is our acidified potassium dichromate 6 or our K2Cr2O7 plus the concentrated sulfuric acid. That's what we make the acidified from. And after we get this full oxidation, we can undergo fractional distillation just to obtain the pure carboxylic acid so that we don't have anything left over from our other reactants that may not have completely reacted. As we've seen previously, the oxidizing agent is always represented by this O into brackets. So some examples could be propan 1-ol, if we have our primary alcohol, plus the oxidizing agent, and because this is a two-step reaction, it requires 2 moles of the oxidizing agent, and that would form propanoic acid. So we have our propan 1-ol, our primary alcohol, giving you the propanoic acid. And you should be able to write either the full displayed formula, the short and structural formula like this, or even the skeletal formula for these reactions. Of course, not for the oxidizing agent, you always just simply write that as O in brackets. We can also have this from an aldehyde, so we could have propanal, which would be CH3CH2CHO, so our aldehyde group. This time it's only a one-step reaction, therefore we only need 1 mole of the oxidizing agent, and again that's going to give you the propanoic acid. Both of these reactions are always done under reflux, of course. Now, another way that we can actually prepare a carboxylic acid is one that we may not have seen before, and this is where we take a nitrile and we hydrolyze it. So a nitrile contains this CN group, so the carbon triple bonded to a nitrogen. And we can hydrolyze these molecules by heating it under reflux, either with a dilute acid or with an aqueous alkali. So we've got acidic hydrolysis or alkaline hydrolysis. So if we look at an example of each of them, if we start with propane nitrile, so that means that we've got 3 carbons, one of them being the carbon that's present in our CN group, and we're going to add some acid. Now that could be hydrochloric acid generally, but it could also be any other strong acid, so something like sulfuric or even nitric. And of course, we're also adding water because it's a hydrolysis reaction, and this will form propanoic acid. And it also forms NH4+. So we've lost that nitrogen from the nitrile, and we're forming this NH4+ or our ammonium, and that would react with the anion from the acid. So if we used hydrochloric acid, we would make NH4Cl salt. But of course the Cl- would be a spectator ion, so we don't include it here. But the acidic hydrolysis, the most important part, is it is a one-step reaction. Now when we carry out alkaline hydrolysis, it's a little bit more complicated. So we're going to look at an example with butanoic acid. So our formula is CH3, CH2, CH2, Always remember that the nitrile does contain one of your carbons. This time we're adding OH-, and this is typically in the form of any strong alkali, but most regularly it is sodium hydroxide. And we're adding in the water because of course it's a hydrolysis reaction. This time, rather than going directly to the carboxylic acid, what we form is actually the carboxylate ion. So we have our CH3, CH2, CH2, and this time it's COO- plus NH3. Now, of course, the carboxylate is not our preferred not our preferred product, therefore we have to convert this, so it requires a second step where we take our carboxylate and we react it with a small amount of an acid, again any strong acid, typically hydrochloric, and this time we will convert it into our carboxylic acid, and in this case it is butanoic acid. So the main difference between the alkaline and the acidic hydrolysis is acidic is one step, alkaline is 2 steps, because firstly you make the carboxylate and then you have to protonate it. This comes up quite a lot in multiple choice questions where it will ask you how you could form a carboxylic acid in a one-step reaction, and they'll give you a couple of different examples, and you always need to make sure that if it's a hydrolysis, you're looking for acidic hydrolysis. Now we want to look at the 4 key reactions that we have to know for carboxylic acids. Luckily, we do not need to know any of the mechanisms for these. You simply have to remember the reagents, the conditions, and the products. So it makes it slightly easier for you. So the 4 main reactions are a reduction reaction, a neutralization, a halogenation, and an esterification. We will then also, in topic 15D, go into more detail about acyl chlorides and esters. So we will touch on them further about how they react, and they are known as carboxylic acid derivatives. So the first type of reaction is a reduction reaction, and this is where we can go from the carboxylic acid back to the primary alcohol. Now, we cannot form aldehydes using this method because the aldehydes are very easily reduced. So what happens is when you form the aldehyde, it automatically then goes to the primary alcohol. So if you want to get an aldehyde from a carboxylic acid, you require a 2-step method. You would have to reduce it back to the primary alcohol and then oxidize that. So that would require 2 steps. If you want to make the primary alcohol, you would simply use a reducing agent, which is the same one that we saw back in topic 15B, which is LiAlH4, and that is in a solvent of dry ether. And the example that we want to look at now is butanoic acid. So we have our CH3, CH2, CH2, and then our carboxyl group, plus our reducing agent, and this is a two-step reaction, so we require 4 hydrogens being added in total, and we're adding a hydrogen to the oxygen and the carbon of the carboxyl group. So we've got our CH3, CH2, CH2, CH2OH, plus, of course, water. Our second reaction is a neutralization reaction, and this is where we take the carboxylic acid, which we already know is a weak acid. We learned that back in topics 14a and 14b. And so they will be fully neutralized when they are reacted with an aqueous alkali, which is generally a strong alkali, such as sodium hydroxide or potassium hydroxide. As with any neutralization reaction, our products are salt plus water, but we're going to be just slightly more specific, and we're going to say that we're making a carboxylate salt plus water. So remember, that is our oxygens with our delta negative and our negative charge being shared over the two. And these salts can be used in various different applications. So the best example we can give is ethanoic acid, so CH3COOH plus sodium hydroxide, and that is going to react to form the sodium ethanoate plus water. And we've seen this reaction particularly when we're looking at buffers, because we have a buffer reaction when we've got that large reservoir of our acid plus our ethanoate here for the salt. So we've seen this reaction in a little bit more detail. And the general formula for any of these sodium carboxylate salts is the RCOONA. Notice that the metal comes second this time to show that the metal is actually bonded to the oxygen, not to the R group or to the carbons. The third reaction is looking at halogenation. So this is in particular chlorination. So we can do a reaction for the carboxylic acids with any of the halogens, but the one that you will be asked to focus on is the reaction with chlorine, and this forms an acyl chloride that has the COCl functional group. So we take the OH from the carboxyl and we replace it with a chlorine. And as I said, we will look at that in a little bit more detail in topic 15D. What we need to know here is the reagent. So we have PCl5 or phosphorus 5 chloride as our reagent in anhydrous conditions. We will get 2 liquid products that we can separate by fractional distillation, and we get a gaseous product being formed, and that shows as misty fumes. So hopefully you remember from your chemical tests that means we must be making HCl. So to give you an example, if we have propanoic acid, and we add PCl5, we're going to make propanoyl chloride. So the main difference here is that our OH group at the end has been replaced with a chlorine, and we make POCl3 and HCl. Those are the standard products every single time. The only thing that will change will be the carboxylic acid and the acyl chloride that you will make. The other 3 will always be formed. And the general formula of these acyl chlorides is RCOCl, and they have the suffix this time of OYL chloride, like propanoyl chloride or ethanoyl chloride. But we will look at them in more detail in topic 15D. The last reaction that we have to know is an esterification reaction, and this is how we form an ester, sometimes also known as a condensation reaction, because we're going to make water, and it requires the carboxylic acid to react with an alcohol and an acid catalyst, which is typically sulfuric acid. Now, esters are very, very important in industry. They are used in many different applications, such as solvents, or even to make polyesters, which can be used for plastics, such as plastic bottles, or even fabrics, where we get polyester clothing. And they also have very distinct smells and very distinct tastes, so they can actually be used in perfumes or in flavourings. And again, this is a derivative of carboxylic acid, so we will look at them in a little bit more detail in 15D. But to give you an example, we've got methanoic acid, which is HCOOH, reacting with ethanol, which is CH3CH2OH. And these two things are going to form an equilibrium, and we'll look at that in a little bit more detail in the next topic, and we form ethyl methanoate. And what actually happens here is we lose the OH group from the carboxylic acid, and we lose the hydrogen from the hydroxyl of the alcohol, and the two things join together. So we end up with HCOO, CH2, CH3 plus water. So the general formula here is RCOOR prime. And this part comes from the acid, and this R group comes from the alcohol. And when we name them, we have the names in two parts as well. So the first part of the name comes from the alcohol, and the second part of the name comes from the acid. And we will look at that in more detail about how we draw them and name them in topic 15D. So let's finish off by looking at some past paper questions on the carboxylic acids. So firstly, we have under suitable conditions, butanoic acid will do what? So will it react with acidified potassium dichromate to form butan-1-ol? Well, no, because acidified potassium dichromate is an oxidizing agent. If we want to make butan-1-ol, we would need a reducing agent. So B, does it react with phosphorus 5 chloride to form 1-chlorobutane? No, because we just said that when it reacts with phosphorus 5 chloride, we form an acyl chloride. So chlorobutane is not our product. For C, we'll form butyl methanoate when it reacts with sulfuric acid. Again, that has to be no, because the sulfuric acid is a catalyst to form the ester. But if we have the butanoic acid reacting with sulfuric acid, we will not get our ester. So just to check, the answer must be D. So when butane nitrile reacts with hydrochloric acid, that's acidic hydrolysis. So yes, that is our answer. For question 2, we want to look at what ester is going to be formed. So the way we do this is we split it down the centre here, and the left-hand side is going to be our acid, the right-hand side is going to be our alcohol. So we've got 1, 2, 3 carbons on our carboxylic acid, so that must be propanoic, so we can automatically get rid of B and D. For the alcohol, we know that the OH is not on the end because we've got 1, 2, 3, 4 carbons in our longest chain. So we know it's going to be butanol, and we just need to figure out the positioning of the chain and of the OH. And the OH always takes precedence. So the OH should be on the lowest possible number, which in this case will be 2. So our chain is on carbon number 3, giving us an answer of propanoic acid and 3-methyl-butan-2-ol, because we would number it 1, 2, 3, 4. For question 3, this is one that I mentioned earlier, does come up quite a lot. What reaction may be used to make carboxylic acid in a single step? We should automatically be thinking acidic hydrolysis, so that's got to be either A or B, and the hydrolysis of an ester with hydrochloric acid, yes, would be our answer. B is going to require 2 steps. C would give us a diol, and D was one that we've not looked at yet, but it would give us an amide, and we'll look at that in the next topic. So question 4 is then looking at butanoic acid, and you'll see that you get some information about butanoic acid. So it's got an unpleasant smell, it can form esters which have very pleasant smells and tastes, and this would most likely be quite a long question, but we've only just picked out the most important parts here. So we've got some reactions of butanoic acid being shown here, and we want to identify by the name or by the formula the reagent and the conditions required for each of the first 4 reactions. So if we go back, first of all, reaction 1 is going from the carboxylic acid to the acyl chloride. Well, we've said quite a few times now that that is going to require PCl5 or phosphorus 5 chloride. Either one would be perfectly acceptable. For reaction 2, we're going from the acyl chloride to an ester. Now, we haven't talked about that just yet, so let's skip that question and we don't need to worry about it. For reaction 3, it's going from the carboxylic acid to the ester. So we've got butanoic acid and we're adding in an alcohol, and the alcohol will be formed from this part here, which is the OH and one alkyl group. So that's going to be methanol, or CH3OH. Reaction 4 is going from the carboxylic acid back to the alcohol. So this is going to require a reduction reaction. And to go back to reaction 3, we also need to say that we need our concentrated sulfuric acid. Don't forget to always put the catalyst, just like I did there, because we do say that we need the conditions. And for reaction 4, it was our reduction reaction. So that would be LiAlH4 as our reduction, and that is going to require it to be in dry ether. And again, that's very important that we do say the conditions there. For reaction 5, the potassium dichromate and sulfuric acid are the reagents. How do we do this to make sure that the main product is butanol? So if we go from the alcohol to the aldehyde, how do we make sure? Well, it's purely distillation, and we distill the product out right away, because we don't want it to undergo a complete oxidation. We want to make sure that it's only partial oxidation to give us our aldehydes. And then the last question suggests why butanol is not made from butanoic acid in a single step. So we went from the butanoic acid to the alcohol back to the aldehyde, and that is simply because butanol is more easily reduced than the butanoic acid. So our carboxylic acid is less easily reduced than our aldehyde. So our aldehyde will automatically always go to the alcohol, or we can't stop the reaction at the aldehyde. So we have to just some sort of reference that it can't be stopped. So we have to allow it to go back to the alcohol and then oxidize it. So there's the answers to the first few questions, and you can see how the marks break down. Pay specific attention to this question to look to see what you get for the conditions and which ones you get for the reagents. And then the last set of answers as well. That's everything for topic 15C, carboxylic acids. If you do have any questions, please feel free to leave a comment below, and we hope to see you back soon for the next video.